Okay, I'm playing it. Is that okay?
Yeah, just to you.
Can I just?
Yeah, if you want.
Wait, do you want to speak over the?
Yeah.
Oh, okay.
I just saw it for now.
Like the video is going to.
I can restart it. Okay, now if you can start.
Okay.
You can. If you don't want to.
Can I start the
Yeah.
video from the beginning?
Yeah, Martina, please restart and then you go.
Yeah, go for it.
Okay. We present our work, VIRDO, a visual-tactile implicit representation of deformable objects. And think about yourself cleaning rooms and cooking. Tool use are common in our day-to-day lives, and many of them deforms. So the research goal of our project is to derive a deformable object modeling that has visual tactile representation that predicts geometry in contact, and it's also compatible with common robotic sensors. At a high level, VIRDO decomposes deformed shape representation into a deformation field and a nominal shape representation. Here, the nominal shape is a geometry of an object takes in the absence of external forces. This is the architecture of our model. In the left panel, we visualize the inputs of our network, which are reaction force, point cloud, and contact locations. In the right panel, you can see a shape reconstructions using our implicit representations. In the middle panel, we visualize our network, and it has two subsections. One is about representing nominal shapes using object model, and the other is about representing deformation field using deformation module D. So these are the reconstructions using a single pre-trained VIRDO. And I want to highlight that VIRDO can represent multiple objects and their deformations. Also, given the same contact location, VIRDO can produce a unique deformation field from the tactile signatures. And also, VIRDO can be generalized to unseen contact formations that are within the distribution of training data set. This is an important functionality in robotics, given a wide variety of interactions. Also, however, it's not trivial to get a contact patch explicitly. So instead of getting the contact patch, we can use a partial point cloud to perform a geometric estimations under occlusion. Here, the reconstructions at time step 0 is when the vision is missing. So I want to highlight that even when we are using the tactile only, the geometric estimation is fairly close to the ground truth. Also, our method can learn dense correspondence without explicit supervision. So for this figure, we first painted the nominal shape and tracked the painted points by applying a variety of deformations. And this property is useful for tracking a pose and relative deflection of a point during robotics manipulations. Finally, we visualize the latent space using view map projections. And in the left panel, we visualize the object code, and it exhibit a separate and even separations. However, if you visualize the first codes, it's naturally distributed according to their bending directions, and it's generalized across different objects. And finally, if you visualize the concatenated vectors, you can see that it's clustered by their deformation properties like stiffness that are not directly observed or given as input. Thank you so much.
Any have questions? Then I have actually a question about the applicability of this method. You seem to focus on these like spatular elastic type objects. Now we have heard a lot about linear deformable objects, ropes, or clothing. How is that extendable? Or?
Yeah, that's a great question. So, for example, if you are manipulating chains or ropes, we found that it can be elastic under gravity. So in this case, we can apply our methods to the rope manipulations.
Thank you very much. And we're gonna continue with the next spotlight talk. I think Haochen, she?
Yeah, right.
Yes, okay.
I'm on Zoom. Yeah.
All right, perfect. Then you can play the video.
Hi everyone, my name is Haochen Shi. I'm a first-year master's student at Stanford University. Today, I'm very excited to share our recent work on deformable object manipulation, which mainly focus on manipulation of elasto-plastic objects, such as plastic or Play-Doh. Our task is to let the robot use a parallel two-finger gripper to deform an elasto-plastic object, such as a Play-Doh, into a target shape, such as the letter X on the top right corner. It's a very challenging task to manipulate the elasto-plastic object into a target shape for the following reasons. Firstly, the real-world input from RGBD cameras is very noisy. Secondly, Play-Doh has high degrees of freedom and therefore very complex dynamics. Thirdly, the action space of this manipulation task is very large. Therefore, we propose RoboCraft to tackle these challenges. The result of shaping X by RoboCraft is shown at the bottom right corner. RoboCraft includes 3 modules: perception, dynamics, and control. We will work through them one by one. Graph neural network needs clean and sparse data to learn a particle-based simulator, but the raw RGBD images from vision sensors are very noisy and dense. So how to tackle this problem? In the perception module, we reconstruct a watertight mesh around the raw point cloud and sample a sparse point cloud inside the mesh as the input to our graph neural network. After preprocessing the data in the perception module, we use the graph neural network to learn the dynamics and predict how the particles will move when applying an action. We demonstrate in our work that 10 minutes of real-world interaction data is sufficient for the graph neural network to learn the complicated dynamics very well. The last module is model predictive control, with the trained graph neural network as a dynamics model. We use a random sampling and gradient-based trajectory optimization method to find the robot trajectory that leads to the most similar shape to our target. Next, we will show our results in the simulation. In the simulation, RoboCraft successfully shapes most of the letters in the alphabet. Some of them, such as C and E, are in fact very challenging, but RoboCraft is able to figure out a good trajectory to complete the task. Next, we will show the experiment results in the real world. RoboCraft successfully shapes the letter X in the real world. It accurately predicts how the Play-Doh will deform and leverages the gradient information to plan the best trajectory, which is vertical pinch combined with horizontal pinch. Here's a more challenging task: manipulating the letter A in the real world. If you were asked to shape an A, how would you accomplish the task? Although the shape of A doesn't seem very complicated, it's actually hard for me to quickly come up with the exact steps to do it. RoboCraft instead figures out a creative solution that differs from what I have in mind, but nicely completes the task. Following the question of how to shape an A in the last slide, here's a comparison between RoboCraft and untrained human subjects in both the simulation environment and the real world. You can see that RoboCraft is comparable to and sometimes better than human subjects in the tested tasks. Thanks everyone for the attention.
Thank you. Are there any questions? Yeah, please just come here. It's easier with this microphone, so you can hear you.
Hey, oh, great talk. I was wondering if you thought about deforming the object on a horizontal plane, like along the plane on which the thing is sitting.
So if sorry, can you hear me?
Yeah, I can hear you.
Okay. So the question is like, manipulating the Play-Doh into a target shape in a long horizon. Is that the question?
Like if I can see my hands, I guess you're doing this. What about doing this?
So sorry, can you raise your hand higher? Yeah.
So you're doing this.
Uh-huh.
What about doing this?
Oh, yeah, that's a great question. So, okay, yeah, thanks for the question. It's a very great question. So, in this work, we are mainly focused on like grippings with the grippers vertical to the plane. So it's 2D grips, and in the complete version of the paper, we also explore 3D grips, like allowing the gripper to rotate on the plane. So it has some angles to the it's not vertical to the plane. It also has some angles, and our RoboCraft is also able to deal with those situations. Those are for sure more complicated and more challenging tasks. So yeah, we mainly focus on grips like this, vertical to the plane.
One more question.
Yeah, so how accurate is your graph neural network in just predicting the dynamics? Like, did you do any experiments to see whether it predicts the deformation as the amount of deformation that actually happens in the real world?
Okay, so the question is about the amount of so the question is about how the graph neural networks work in the predicting those deformations.
Yeah.
Okay, yeah, so I guess empirically, I think our graph neural network is able to predict the dynamics in a long horizon very well. And also since in the real world, we don't have the precise physical parameters of the Play-Doh, and it's also hard to predict those parameters very accurately. And our graph neural network has better performance than simulator based on material pooling method on the real world experiments. Yeah.
Thank you very much.
Thank you.
Continue on with the next spotlight talk by Gautam Salhotra. Yeah, come here and we can play the video.
Hi, my name is Gautam Salhotra, and in this video, we present our method Deformable Manipulation from Demonstrations, or DMFD, to solve robotic manipulation tasks on deformable objects. Many everyday tasks use deformable manipulation, such as folding clothes or cooking. The problem is hard due to the difficulty of obtaining object states and predicting their dynamics, especially since environment interaction can change these properties. Furthermore, their complex dynamics and their high-dimensional configuration can increase the task difficulty. Analytical techniques succeed in certain conditions, but fail to generalize with such tasks. We propose a new method, Deformable Manipulation from Demonstrations, or DMFD, for an agent to use experts' data while learning to solve deformable manipulation tasks. It is designed to work with state and image-based observations with both 1D and 2D deformables, and in both simulation and the real world. Now let us look at the DMFD training pipeline. So here we see that the agent obtains observations from the environment during experience collection or the replay buffer during training. For the state-based environments, the observations are encoded by an encoder network. Then the state encoding is passed to the actor and the critic, denoted by the blue and black arrows. Note that the observation for the actor and critic is the same as the state observation. Our method can additionally use image-based observations denoted by red. Here we see that the image observations are cropped and encoded by a CNN. The image encoding is then passed to the actor and the critic, denoted by the red arrows. However, for image-based environments, the critic is privileged because it also receives a state encoding while the actor does not. This state encoding can be seen here in the solid black arrow. Specifically, our method uses expert demonstrations in 3 ways. 1, we pre-populate the expert buffer with pre-populate the replay buffer with expert trajectories before training. We leverage an advantage-weighted formulation for the loss function, encouraging the agent to match with the expert actions in the replay buffer. But note that we add an exploration term that we balance with this loss. And finally, we employ a reference state initialization probabilistically, where we reset the agent to a state along an expert trajectory. Then we compare the state trajectories of the expert and of the agent to create some sort of imitation reward. Our method has 4 main contributions. First, to encourage wide exploration, we add an exploration term to the advantage-weighted loss. To deploy our method in the real-world settings, we actually extend this framework to the image domain using CNNs and data augmentation. Second, we introduce probabilistic reference state initialization that I just mentioned before. We do this during experience collection, where instead of always resetting the agents to states seen by the expert, as is done in RSI, we invoke this concept probabilistically to promote exploration and learning in states that are difficult to reach. Third, we create 2 new simulation environments for cloth folding with 1 robot arm. We deploy DMFT on a real robot and observe that we have a minimal sim to real gap, indicating that it can actually work in real world settings as well. And finally, DMFT outperforms LFT and non-LFT baselines on both the state and the image-based environments, and for both 1D and 2D deformables. Next, we discuss the results of the image-based environments. So for the straightened rope task, we see that DMFT beats the best baseline with image-based observations. In this rollout, our method solves the task with a clean motion, whereas the best baseline still contains a loop. In the cloth fold image task, an agent must fold a flattened cloth along an edge. We see our method beating the best baseline by folding the cloth with almost complete coverage over the 2 halves. Our new environments that we create are the cloth fold diagonal task that requires the agent to fold a square cloth along a diagonal with only 1 end effector. In the pinned corner version, we successfully fold the cloth almost completely over itself, whereas the best baseline kind of struggles with the task. In the unpinned corner version, we have similar success. And we can see that while the best baseline is able to actually finish the motion, is actually able to fold the cloth, it's not actually able to finish the motion. Here we present a real world example or a real world experiment on the cloth fold diagonal task with the unpinned version. But this is a variation with large rotation of the cloth. Our method is also robust to variation in the real world. So we can see these in these rollouts over here. And over the course of all the rollouts we recorded, we have a sim to real gap of approximately 6% or so. In conclusion, our method works on the state and image observations and is able to outperform LFT and non-LFT baselines. It is primarily because of the ways in which we use the expert data and balance it with exploration. Additionally, we introduce 2 challenging cloth fold environments and deploy our system on a real robot. Thank you.
Will we ask questions? Yeah, please.
How many demonstrations do you use for this task?
So the question is, how many demonstrations are used for this task? For the original paper over here, we had about 8,000 demonstrations. We managed to find ways to reduce it down by almost 2 orders of magnitude. So we're down to about 100 demonstrations. And we're trying to see for follow-up works how to reduce that further.
Yeah, I have a follow-up. So I'm wondering about if you've analyzed like the distribution of demonstration data, like if you've analyzed how many demonstrations are hitting that corner or the edges but not corner, like have you done that analysis?
The way we created demonstrations was we actually reset to a bunch of variations, and then we have a sort of algorithmic expert that would solve the task. That being said, we did not check how many of those expert demonstrations were for individual corners and how many were not. But this would be a great thing to verify this, to see the distribution of where the experts choose to pick into this.
Yeah, one more question.
You also use some reinforcement in the baselines. How did the reward look like for these experiments?
Yeah, actually, there are a lot of plots in that. It's in the poster, so it's going to happen in 10 minutes. You'll see the poster. In a lot of the baselines, we saw anything that did not use demonstrations was understandably performing not as well as some methods that were using demonstrations. In fact, in many of the rollouts I showed over here, the best space-time was always mostly something that used some sort of demonstration. And so the exact graphs I can show it to you in the poster, and it's also in the PDF that's in the paper.
Did you use a dense reward or only a sparse reward?
Oh, I see. It's dense reward. It's a dense reward for every step.
Dense rewards, you found that none of them were able to complete the task.
They were able to complete the task, but many a times there's a performance metric to what degree you complete the task. So for example, to what degree you're able to fold the cloth, let's say along a diagonal or along an edge. And in that sense, they were not able to perform as well as our method or some of the other baselines as well in the same, for the exact same task. So they do sort of complete the task, but it's the completion is not binary. There is a performance metric. Yeah.
Thank you very much.
Thank you.
Brings us to our next spotlight talk. Alex from CMU. I see, perfect. Daniel, you can play the video, Martina.
Hello, my name is Alex LaGrassa, and the title of my talk is Planning with Model Preconditions for Water Manipulation. Although deformable objects are difficult to model, model-based planning is still a useful tool for many tasks involving deformable objects. For example, pouring, shaping dough, rope manipulation, and cloth smoothing. In this example, the robot is watering the houseplant and it can't spill water on the floor. For a movement in free space using a controller that's slow enough to avoid sloshing, a simple rigid body model is accurate enough to model the effects. However, if the robot is pouring the water over the leaves, a more complex model such as a simulator is necessary to model the interactions between the water and the leaves. The task can be completed without modeling those interactions by using a special purpose model such as a simple learned model or analytical model for pouring near the base. Our problem statement is then to learn model preconditions for various different models and also use that information to plan and use models where they are accurate. To do this, we use model preconditions, which are regions of state action space where a model is predicted to be accurate. For example, transition A is not accurately modeled by any of these models. B can be accurately modeled with a simulator, and C can be modeled using a simulator or a learned model. In this work, we learn a model using data, then learn the corresponding model precondition, and then finally, plan using those model preconditions to only use transitions that are predicted to be accurate. The tool we use is a model deviation estimator, or MDE. An MDE predicts the deviation, which is defined as the distance between the predicted next state of a model and the actual next state. The model precondition is then defined as state action pairs where the probability that the deviation is greater than a maximum deviation, Dmax, is less than some small probability delta. This is the data collection pipeline we use in this work. The system is in an initial state, has some initialized models and a goal distribution. The robot computes plans, executes those plans, and then collects two data sets, alternating left and right. The first data set is to train a dynamics model. Once the models are updated, then new plans are computed, executed, and then used to update the model deviation estimators. And the final result is a planner that can compute plans that are more reliable at test time. This is the process for learning MDEs. The implementation that we use for the MDE is a Gaussian process, where the observations are inputs of state action pairs, and the outputs are the deviation. This is the domain that we evaluate our method on. The state is the pose of the box on the left and the volume of both containers. The actions are to move the left box to a desired XZ pose and to rotate about the XZ plane. The tasks are box at location, which is to move the control box to a given location, and water in box, which is to pour a given volume of water into the target container. No more than 1% of the initial volume of water can be spilled. It occurs in box at location when the box hits the target box and then water spills. Model error occurs in water in box in the transport by moving too quickly and the water coming out, but also by not pouring the desired amount. Here we show the success rate in finding plans using model preconditions and without using model preconditions. On the left, you can see that the success rate in finding plans does go down using our method, and that's because it's more constrained. However, we do find that the success rate when executing those plans is much higher when using model preconditions than when not using them. In conclusion, we've shown an improvement in plan performance by using these learned model preconditions, and that deviation estimators can be used on learned models. Our next steps are to scale to larger dimensional state spaces, which are important for representing many deformable objects, and to assess the ability for this approach to improve data efficiency over existing methods, especially over predicting error in state space. We also anticipate many challenges in applying this to the real world, as data is much more expensive and the state is difficult to observe. If you're interested in discussing this further, please visit my poster or contact me. My email is on the bottom right. Thank you. Hello, my name is LaGrassa.
Yeah, do we have questions?
I have a quick question. I'm curious about the choice of the Gaussian process for modeling. Did you consider any alternatives, or did you right away think this was the right thing?
Can you just repeat it?
Yes.
Yeah, which microphone?
This one, the big one.
Thank you. I've actually used many different implementations for them. I tried using nearest neighbors. I used the neural net. I tried representing the uncertainty in the neural net. GPs ended up being the easiest choice. They're data efficient. The ability to, sorry, I forgot to repeat the question. The question was, why did we choose a Gaussian process as the implementation, and if we considered other models as well? And the answer was data efficiency, having a well-defined and easy to work with representation of uncertainty. And that made it easier to select both what mean we want and balance on the probability of the error being below a certain threshold. And does that answer your question?
Yeah.
Okay, thank you.
Should I come up to the mic? Yeah. Okay.
Yeah, so the question is, it seems that because there's such a huge variety of geometries and leaves and houseplants, it would be almost impossible, even in like the ideal setting, to water 100% of them without spilling any water. What do you think the upper bound percentage would be in the ideal case that like you could hit for this kind of problem? Because I've not even thought about this problem before, so it's kind of an interesting space of things to think about with leaf geometries and such.
Do I need to repeat this one?
Yeah, just put the limits.
I mean, is it repeated on the mic? Okay. The question was if what sort of success rate would be acceptable for a watering task, and how to address the difficulty of modeling the wide variety of leaves. Is that an accurate representation? I think the desired success rate is a very user-dependent question. So that would depend on what the requirement is. So for example, if a little water is okay in a house, that would be specified by the user. I think that getting a high probability is not out of question, because there's ways of watering that doesn't require it spilling on the leaves, for example. And that's one thing that I hope to address in both reasoning about model error and in incorporating that into planning. Does that answer your question?
Thanks.
Sure. Yeah, thank you very much. This brings us to our last spotlight talk from Rika.
Priya is online as well.
Oh, it's online, okay. So we have 2 people to answer questions, and let's play the video.
We present DiffCloud, real-to-sim from point clouds with differentiable simulation and rendering of deformable objects. First, we will describe DiffCloud inputs. Our hardware setup consists of a Kinova robot and 2 RealSense cameras, one mounted on the side and one overhead. Next, we manipulate deformable objects and record point clouds from both views. Using knowledge of the geometry, kinematics, and meshes of the Kinova robot, we also mask out the robot from point cloud frames such that only the deformable object is captured. The merged point clouds serve as input to DiffCloud. The goal is to estimate unknown physical parameters of the object, such as stiffness and mass. We use a mesh-based deformable simulator. In simulation, we execute the same trajectory on the deformable object which was performed on the real robot, resulting in a deformed state. From this state, we differentiably sample a point cloud from the surface of the mesh. Next, we take the loss incurred between the simulated and real point clouds. Since the simulator and the point cloud sampling procedure are both fully differentiable, we can propagate the gradients to the estimated simulated parameters and perform updates. We repeat these 2 steps until point cloud alignment is achieved, indicating that we have found simulated physical parameters that fit the observed real point clouds. We evaluate DiffCloud on 2 real scenarios, starting with lifting a cloth off a table. We show the real point clouds for a stiff, lightweight paper towel and a heavy, collapsible polka dot patterned cloth. On the left is the target input point cloud sequence, and on the right is the result of visualizing the simulated cloth with the parameters found by DiffCloud as point clouds. We find that the inferred parameters produce point cloud alignment between real and sim, noting that DiffCloud correctly learns the shape retention and self-collapse behaviors of the paper towel and polka cloths. Next, we move on to fold. Similarly, we show the trajectories for 2 cloths of very different properties. We note that the fold scenario exhibits a high degree of self-occlusion and partial observability. Nearly half the cloth is not apparent in the point cloud due to the resting half of the cloth being indistinguishable from the table surface. Still, DiffCloud finds parameters that fit the observed trajectories and learns the shape retention versus self-collapse properties. We also evaluate DiffCloud on 2 simulated scenarios using synthetic data as input, band stretch, and vest hang. In these experiments, we will visualize the initial guess for parameters that DiffCloud starts from in black, and compare this against the final optimized parameters in blue. 2 target sequences for band stretch are shown in green, where varying the band properties affects distance traveled upward along the pole. DiffCloud successfully finds these parameters, shown in the blue column. On the right, we see that DiffCloud starts from an initial guess for parameters shown in black, which diverges from the target behavior in green, but eventually converges to optimized parameters in blue, resulting in alignment with the target. For vest hang, we show a highly deformable and shape-retaining vest, with the properties affecting the resting pose of the vest on the pole. DiffCloud learns to infer parameters that describe these behaviors. Thank you so much for listening, and for more information, please feel free to check out our website or stop by our poster session later today.
Any question?
Yeah, please ask.
Yeah, so the question is, do you need to learn the parameters of the simulation for each object separately, or can you learn a generalized model that can represent maybe like multiple shapes of deformable objects?
So that's interesting. In this work, right? The question was, can you learn a generalized model that would kind of infer the properties of multiple objects as opposed to a single object? So in this case, we tried for a single object, and that was specifically to infer the parameters of infer the parameters so that you match the motion of a given object. It's an interesting question as to in what cases would you want such a thing, right? Because you wouldn't be then manipulating a given object, right? You would be like manipulating an abstract group of objects or something like this. So you can certainly do it very simply by just feeding a lot of data from multiple trajectories of different objects. You would you would find something. The problem, of course, is what happens if you have objects for which some group of parameters would be optimal for one of them, and then another group of parameters would be optimal for the other one. So for that, right, I would refer you to what I was saying before about treating these things as probability distributions, both on the inputs and the outputs. And so then you could certainly do this. However, we did not do it in this particular work. And I think with differentiable simulators, a lot of the focus is, as I was mentioning before, on can it be precise and can it offer more precision than what we can have with the black box. So like a lot of the motivation is really for, can I match the behavior of this particular object, not just a general clause. And that's why the focus is on that.
Right, thank you.
So is the differential simulator, is it explicitly learning parameters about the object, like its level of tension and weight or something? Or is it explicitly learning to a parameter based on those parameters?
It's explicitly learning the parameters, so you would have differentiability with respect to some parameters, and those are the parameters that you would be adjusting, right? And what do you mean by implicit? Oh, sorry. So the question was, whether the learning process is learning explicitly to infer the parameters of the simulator, or is it learning something implicit? And so I'm asking, what is your idea for this?
Yeah, like if you had like a piece of rope, like the weight of it will affect how it gets simulated. Like, is the simulator learning sort of interpretable properties of it?
Yes.
Or, okay.
Yes, it is learning interpretable properties in the physics that you have coded for, okay, this rope is moving and the physics parameters for its motion for the model of that. Yeah.
Thanks.
One more question?
Did you face the issue that multiple sets of parameters can fit a particular motion?
That's interesting. Let's see if Priya is around. Maybe she, yeah, I'll repeat it. So, so the question was, did we face the issue? Oh, can we have her? It's great. But
if she speaks up.
Oh, she speaks up. We can hear her. Yeah. Did we face the issue of what happens if you can have multiple parameters that would be a good description for the motion of the, to match the properties of the object?
Yeah, that's a great question. So we did face this issue, especially like since we're considering the parameters of stiffness and mass, there are like some scenarios where high stiffness could overcompensate for low mass and vice versa. But I think in this work, we're mainly concerned with not so much like finding the exact stiffness and mass parameters that correspond to like the real quantities on the physical object, but just learning simulated models that could fit the real behavior by finding really like any valid combination of the stiffness and mass that would yield point cloud alignment. But it's definitely an interesting question. And in follow-up work, it'd be interesting to consider maybe different sets of physical parameters like friction, mass, and things that don't necessarily have or yield like similar deformation results on the objects themselves.
Yeah, thank you. And a follow-up question, does like the same set of parameters generalize to like many different motions of the cloud?
So in general, we did find that one thing that we didn't do in this work, but we would definitely want to evaluate in follow-up work is like whether, for example, like the found trajectories from lift would then yield comparable behavior on the fold task. And we did see some general patterns like the stiffness and mass parameters found from lift and fold yield similar results across tasks, but may not be like exact parameter matches, but definitely like fitting parameters based on one trajectory and then evaluating across tasks is something we'd like to do going forward.
Thank you very much. That concludes the spotlight.